Hey guys, this is a bit of a quick video today. It is not going to be quite in-depth because I believe that other YouTubers such as 3 Blue 1 Brown have covered the basis behind this topic in much more detail than I possibly could at the moment, especially due to the prevalence of sort of animation software. So I'm going to link to 3 Blue 1 Brown's video in the description to help you build up your knowledge as to why I'm describing what I'm about to describe to you in the way I do. So the issue I wanted to talk about here is thinking about the unit vectors I and j, or I hat and j hat. And basically, you guys already know that I and j represent the vectors 1, 0 and 0, 1 respectively, where this is a sort of, the first one is unit movement to the positive x direction, and this is unit movement to the positive y direction. And the reason I wanted to say this is because there are two things I'd like to cover in this video. And the first thing is a way of thinking about vectors based on what we know about the number line, which I'm going to call the 1D number universe, basically, because vectors live in a 2D number universe. And I'll explain what I mean about that later. And the second thing I wanted to talk about is the assumption that I and j are your basis vectors. And what do I mean by basis vectors? Well, this is also explained in a video I'll link in the description, but it basically means the vectors which make up the reasoning behind your column vector notation. So the reason I said in the title that I and j have a sort of monopoly on column vector notation, or that they do not have this monopoly, is because I wanted to make it clear that the two vectors that, like, this is 1 times I plus 0 times j, it doesn't have to be I and j, and I'll go into more detail about that later as well. So the first thing, a way you can think about vectors. So say we have the number line that you dealt with in primary school. You have your 0, which is basically the origin of this line, this one-dimensional space, and you think about a number like positive 4, and it's usually represented as a point 4. But I want you guys to think about 4 as a vector going from 0 to the point where a location vector for 4 would be on the number line. So this whole vector it's like a one-dimensional vector for 4, where you're only working with the sort of I hat that exists in the 1D universe, the number line, which of course is just like the number we call 1. There really isn't anything more to it than that. And so you could consider positive 4 to be a vector with the direction positive and magnitude 4. And of course, that means negative 4 could also be seen as a vector with the direction negative, or negative x if you want to call this the x-axis, even though there's only one axis, so it's not really an appropriate term. You've got negative 4, which can be treated like a vector with a direction negative and magnitude 4. And why am I putting the brackets around this? Because I want to show some similarity to the column vector notation of like 0, 1, 3, 5, whatever. Any real number that we think about can also be thought about as a one-dimensional vector from the number line. So that's one insight about vectors that I wanted to share with you guys. Because 2D vectors which you guys are dealing with in Further Pure Mathematics and probably in other mathematics courses as well, like American High School or whatever. 2D vectors exist on the number plane as sort of multiples and sums of the unit vectors I and j, because while we only have 1 as our unit on the number line, the two-dimensional universe has a unit in the positive x direction, I, which you are familiar with, and j in the vertical direction. And thinking about vectors as 2D numbers based on some I and j, so like if this was 3, 5, then this would be a vector made of 3 I units and 5 j units, or 3 units in the direction of the positive x and 5 units in the direction of positive y to make our vector. Then that is in a really similar way to how we can think of just the number 4 as being comprised of 4 I units, or 4 ones, where 1 is our only unit vector in the number line. So yeah, that's what I wanted to talk about in this scenario. The difference between 4 as a one-dimensional vector and 4 as a scalar is that this 4 can often represent something in physics. So it can represent a real thing, but the scalar 4 does not really mean anything except for the fact that it's an abstraction of having 4 things, like 4 cookies, 4 ducks, 4 boxes, whatever. Doesn't matter, because 4 is just the abstract concept used to model that many things, right? And of course this scalar can be multiplied by a vector to scale it up, give it bigger magnitude, so on. But this vector, one-dimensional vector 4, which again is something that we would deal with in, say, a physics problem where we're only looking at things in one dimension, or especially when we're looking at, to apply it to further pure maths, the particle moving on the x-axis, it would have a velocity vector, a displacement vector, an acceleration vector, all of which are one-dimensional and can be called positive or negative numbers. So really you're doing calculus with vectors instead of scalars in that case. Anyway, enough examples. That's just sort of the point I wanted to get across about two-dimensional vectors. They are numbers, they just have 2 different kinds of 1 to be made out of. Right? So now I want to move to my next topic, which is the assumption of I and j. Basically, I and j are quite fundamental ingredients in the 2D universe to make up all the vectors that we know. But one idea that I think is not really exposed to people during the course of Further Pure Maths, so I want to bring it to your attention now, which will this idea will be explained in excellent and amazing detail by 3 Blue 1 Brown over on his YouTube channel in the video I'll link to in the description. These 2 unit vectors are called basis vectors because they are the basis of what column vector notation is. So like 5, 3 represents 5 times the vector I plus 3 times the vector j, or 5 times 1, 0 plus 3 times 0, 1, where 5 and 3 are scalars, not one-dimensional vectors. And the thing is, basis vectors do not have to be just I or just j. Like, in the one-dimensional sense, say you were talking about like 3 dozen or 3 meters. 2 kilometers per hour. These are all examples of one-dimensional quantities that do not use the mathematical unit 1 or I as their basis, right? 3 dozen, well, it's 36 units, but the basis dozen, or basis vector dozen, meaning 12, if that's not a familiar concept for you, could represent the vector of length 12 on the one-dimensional number line, or just the number 12, right? So this 3 does not actually mean 3 units, but it means 3 of this quote-unquote basis vector, a dozen. 3 meters does not actually represent the abstract concept of 3, but it's 3 multiplied by the concept of a meter. So say if we're looking at a displacement vector, then it's a meter in a particular direction. So really I should be writing like meters up. And meters up is its own kind of basis vector for which 3 is being applied to. And finally, for a third example, kilometers per hour. This idea of a kilometers per hour vector of course needs a direction also, so say kilometers per hour up or down or so on. This is a basis vector to which 2 is being applied. So to extend this idea to 2 dimensions, I would encourage you guys to think about, for instance, any arbitrary vector. Let the 2 basis vectors be A and B, and you must tell yourself that you don't know what A and B are. They're not 1, 0, or 0, 1. They're not anything like that. They're not anything nice, pretty, or convenient. But just think of them as basis vectors, because when you are writing something like 1 plus 3 lambda A minus plus minus 2 plus mu B, and this is the kind of sum in a problem involving intersecting vectors that I mentioned in the thumbnail of this video. For instance, you have like a triangle, a square, and you're trying to figure out how these, what's like the ratio of this side to this side, or this side to this side, whatever. That kind of problem, you'll often get this form. And I want you to think about these vectors in the sense that they could be expressed like 1 plus 3 lambda minus 2 plus mu, which is why you often get a simultaneous equation out of them, because it'll be something like you'll get 2 ways to express the same thing, right? And in many cases this will be sort of like this. You'll get something times A plus something times B is equal to something times A times something plus B. And the reason that you can get simultaneous equations out of this is because each side of the equation is its own vector with A and B as basis vectors. So just how you might get a simultaneous equation from 2 regular old vectors, so say vectors have like x's and y's in them, just how you might get a simultaneous equation from those being equal, that's why you can get a simultaneous equation from these being equal. And if that idea kind of flummoxes you or makes you a bit uncomfortable, then I'd like to give you some visual intuition to it. Because say you have the origin here, and there is only, for any given point, there is only one unique vector that goes to that point. So that means this vector can only be described in absolute numbers based on our unit basis vectors I hat and j hat. 7, 3. Say it's just these constant numbers. They are unchanging. So in any system, even though the basis vectors here are like 90 degrees to each other, and so naturally you might think that that's a condition required to describe the entire 2D coordinate plane with unique position vectors. It's not actually the case, because for any position, say you had a vector that looks like this and a vector that looks like this as your two unit, quote-unquote unit vectors or basis vectors. Think of the number in this unit vector as a horizontal line, and this horizontal line is all the possibilities of how many of the first unit vector you might have. And sliding along this horizontal line is another line angled in the direction of the other basis vector. And you slide this other line along until you hit the point you want. So by sliding these two lines around, you can see that these two lines only intersect at one point, and therefore in a similar way, each individual point can only be described by one unique combination of the two basis vectors, as long as they're not like in the same line or opposing to each other or whatever. As long as they have even the tiniest difference in angle between them, which in the vast majority of these questions they will, because the question needs to work anyway, the two vectors A and B that they give you as part of a shape or something, you can take them as basis vectors and visualize them in this column matrix form as a result of taking A and B as basis vectors instead of I and J, which are our defined and clearly set out unit vectors. So yeah, that's kind of all I had to say on this topic. This is actually a re-recording of a video that I tried to do once and I felt like it didn't go very well, so I didn't upload it. My explanation was quite unclear and stuff. But yeah, if this video helped you and you're thinking about vectors, then please subscribe and stick around for more videos. There are new videos every Sunday, Tuesday, and Thursday, so please stick around for the upload schedule and for the content. If you have any videos you would like me to make, any ideas you want me to give commentary on, or questions you want me to solve for you guys, then leave a comment, or you can now, this is new, you can now email me at watchmedomath@gmail.com. So, yep, that's all. The 3 blue 1 brown video about matrix transformations in regards to using different basis vectors will be in the description, and I hope it helps you guys also, because I think it's really, really good, and I just learned this idea myself a couple weeks ago. So until then, thank you for watching.